Yeah. Hi everyone. My name is Jayashree. I'm BTech first year student from ECB section. Today my LAC PPT presentation is about Jordan echelon form for linear state and input transformation. Now let's go into the topic. Here you can see the contents which I prepared in this PPT. The first one is echelon form. The second one is row echelon form. Third one is reduced echelon form. Fourth one is submatrix, and the fifth one is rank of a matrix. Now you can see this content step by step. I will show here the slideshow so you can observe it. Now let's go. First one, echelon form of a matrix. First we will understand what is the echelon form of a matrix. A matrix is said to be in echelon form if zero rows in any exist, they should be below non-zero row. If the full row is zeros, so that row should be below the non-zero row. That is mean by first sentence. And the second sentence, the first non-zero row entry in each non-zero row is equal to 1. So if a full row is if the full row is filled with zeros, so that full row is considered as a 1. That is mean by second sentence. And the third sentence is the number of zeros before the first non-zero rows elements in a row is less than the number of such zeros in the next row. So this is about the echelon form. Next, and some of the note of echelon form, the number of non-zero rows in the echelon form of A is the rank of A. The number of non-zero rows in echelon form of A is the rank A. The rank of the transpose of matrix is the same as the original matrix. The condition 3 is optimal. So these are some notes we can observe here. And then some of the example here this is a 4 by 4 matrix. At last you can see all the zeros, and third row you can see only 2 zeros, and second row you can see only 1 zero. So this is upper triangular matrix. You can also say that it is an upper triangular matrix, so it is a row echelon form. Now second one is 3 by 6 matrix. Here you can see the third row is a full filled with zeros, and the second row is 0. So it also exists the echelon form. So these are some examples of echelon form. And then you can observe. Next, reduced echelon form. Here, next we will learn about a reduced row echelon form. A matrix is reduced to row echelon form from when it satisfies the following condition. When these conditions are satisfied, then it's said to be a row echelon form. The matrix satisfied conditional for a row echelon form. The leading entry in each row is the only non-zero entry in its column. Each of the matrix should below our example of the matrix is reduced by row echelon form. Here you can see that they are reducing by echelon form because we have to reduce all the rows in all the first columns into zeros. Here you can see that the last row is filled with 3 zeros and the second row is filled with 1 zero, so it is 2 zeros, so it's reducing. You can clearly observe there they are reducing in their zeros forms. So these are some examples: 2 by 4 by 4 matrix and 2 by 2 matrix. You can observe there. Next, the following examples are the matrix in the echelon form. These examples are the matrix. These examples are row echelon form. Here also you can see that the last row is with the three zeros and the second row is with 1 zero. So here also clearly the row is getting reduced. Here in the second picture, I have clearly underlined that the row is the second row is filled with the full zeros, so that you can see I have pictured them also. You can clearly observe it. Next, find the rank of a matrix A. Here we will see the example one. Find the rank of a matrix A. A is a 3 by 3 matrix by reducing it into the echelon form. Given that A is equals to 2, 3, 7. This is the A matrix. Applying row transformation on A. We have to apply row transformation. Here, R1 gives rise R1 minus R3. You have to do that R1 minus B means row 1 minus row 3. Here, R2 gives rise to R2 minus 3R1. Here, row 2 minus 3 row 1. We have to do that row 2 minus 3 row 1, and then row 3 minus 2 row 1, so that you will get 2 zeros on R1 and R2 and R3. Here R2 divided by 7 means row 2 is divided by 7, and then row 3 minus 2 row 1, and then R2 gives rise to R3 minus R2. The row 3 is subtracted from row 2. Then the result is up. You can see that 1 minus 3 1 minus 1 0 1 1 and 0 0 0. Here the last row is they reduce it to all zeros. So this is the echelon form of a matrix. The rank of a matrix is equal to the number of non-zero rows. So here the number of non-zero rows is 1, so that rank is also 1. Example. By using the elementary row operations, we can transform the following matrix A into the reduced row echelon form. Here the given A matrix, so we have to add minus 2 times for the row 1 of A to the row 2 to obtain the change. You can see the change in the given matrix there, and then now we have to add minus 5 times to the row 1 and to row 3 of A to obtain, then it will obtain like this, and then we have to add 2 times row 1 to row 4 of A. So the matrix will be in the first row 1 1 minus 1, and the second row 0 1 2 0 1 2 0 0 0. Here you can see that the third row is all zeros. The third row is fully reduced with zeros, and then we have to add minus 1 times row 2 to the row 3 to obtain A matrix 1 minus 1 1 0 1 2 0 0 0 0 0 0. Here row 3 and row 4 is reduced to 0. By adding minus 1 times from row 2 to row 3, we will get the given matrix. By adding minus 1 times a row 2 to row 3, we will get that. Therefore, we get reduced echelon form from the given matrix to be 1 0 minus 3 0 1 2, and the third and fourth rows are filled with 0. So we can confirm that this is a fact unreduced row echelon form by checking that the projects we mentioned earlier under the leading echelon form of a matrix. So this is an example of reduced row echelon form. Here another example for the matrix, given matrix A. Can be put in reduced row echelon form by using the following elementary row operation. In the elementary row operation, we have to use only the row operation. We should not use any column operations here. If we use that column operations, maybe the equation will be not tallied with the answer. So that we have to do only row operations. Here we have first for the given matrix 2R1, we have to 2R1 plus 2R2. We have to add row 1 to R2, and then the matrix will be appear there. I showed there in the picture, and then minus 3R1 plus R2. You will get that, and then R2 plus R3, and then minus 2R2 plus R2. So the final matrix, you can see that the third row is reduced with zeros. The final matrix in the row echelon form has 2 non-zero rows, and thus the rank of a matrix matrix A is 2. You can observe clearly over there. Step by step, I have given applications also. You can go through it. Find the rank of a matrix A. And this is another example. We have to find the rank of a matrix A for the given matrix solution. The order of matrix A is 3 into 4, 3 by 4 matrix. This is a 3 by 4 matrix. Here, therefore, P of rank of A is greater than 3. Here, the rank of A is greater than 3. The matrix, you can see here tabular form which I mentioned here, the matrix A, and on the right side you can see the elementary transformations. Here R2 minus 3R1 for the first matrix A, and the second matrix R3 minus 2R1 for the second matrix, and the third matrix R3 minus R2. The number of non-zero rows is 3. Therefore, the rank of a matrix also 3. Here, the number of non-zero rows are 3. So that the rank of a matrix also 3. Here, the rank of a matrix. Let A be any M and N matrix. Then A is consist as an N column vectors A1, A2, A3, and so on, AN up to AN, which are M vectors. So these are called as an M vectors. Let's see the definition. The rank of a matrix A is the maximal number of linear dependent column vectors in A, i.e. the maximum number of linear dependent vectors among A1, A2, and so on A. If A is 0, then the rank of A is also 0. If the given matrix A is equal to 0, then the rank of a matrix becomes 0. So this is about the definition for rank of a matrix. You can go through it. Rank of a matrix 2 into 2 matrix. Here the rank of a matrix about 2 into 2 matrix, 2 by 2 matrix. Let us see how to compare 2 by 2 matrix. Example, the rank of a matrix 2 by 2 for the given matrix A, B, and D, D. Rank A is equals to 2 if we get A, and that is equal to AD minus BC. That is not equal to 0. Sorry that by mistake I have given that equal to. You can change it there. 0, since both column vectors are independent in this case. So in this case, the both vectors are independent. And the rank of A is equal to 1. If det A is equal to det A, then if in the previous we have seen that if the given matrix is 0, then the rank the rank will be also 0. You can see over there 2 by 2 matrix is filled with first row is 0 and second row is 0. Since both column vectors are not linearly dependent, but they are a single column vector that is a linear dependent. And this is about the rank of 2 by 2 matrix. Next. Compute rank by various methods. You can calculate the rank of, you can find the rank by using various methods. First one is Gauss elimination. Second one is by determination method like a det. And then second is minor. And fourth is a normal form. In the normal form, you can use any operation like a column operation or a row operation. You will get the rank correct only. So let's go into the first topic, Gauss elimination. Gauss elimination definition. Use elementary row operation to reduce A to the echelon form. The rank of A is the number of previous or leading coefficients in the echelon form. In fact, the private columns are linear in the example. You can see that example. Find the rank of a matrix. So I given one example. Here the A is a given matrix. Use the elementary row operations. Elementary row operations means we should use only the row operations, should not use any column operations. We can see over there. Since the echelon form has pivots in the first three columns. A has a rank R. The rank of A is equals to 3. The first three columns of A are linearly independent. So this is about the Gauss elimination and its definition. You can see. Next, using determinants. Using determinants. Definition: let A be an M and N matrix. A minor of an order K is a determinant of A and K. Then next be the submatrix of A. So if a given matrix A has a M and N matrix, means M into N means that shows the order of a matrix. If A is a minor of A matrix of an order K, then the determinant of K and the X and the K will be the submatrix of the given matrix A. We obtain that the minor of order K from the A by the first deleting M rows and N K columns and then computing the determinant. There are usually many minors of A of a given order. Here you can see the example which I showed there. Find the minor of an order 3 of a matrix A. Example, computing minor. We obtain the determinants of an order 3 by keeping all the rows and deleting one column from A. So there are 4 different minors of order 3. We compute one of them to illustrate. A is equals to the det of given matrix, and then the det of the given matrix is -4. The minor of the order 3 are called the maximum minor of A, since they are 4 by 4 submatrices of A. Therefore, 3.3 is equals to 18 minor 18 minors of order 2, and 3.4 is equals to 12 minors of order 1. So this is an example of computing minor, and the next one. Using minor proportions. Let A be an M into X matrix, means let A be an M into N matrix. The rank of A is a maximal order of a non-zero minor of A. Idea of proof. In a minor of order K is a non-zero, then the corresponding columns of A are linearly independent. Computing the rank. Start with the minor of maximum order K. If there is a one that is a non-zero, that the rank of A is equals to K. If all maximum minors are 0, then rank A is greater than K, is less than K, sorry. And we continue with the minor of order K minus 1, and so on until we and A minor that is a non-zero. If all minors of order 1 are 0, then the rank of A is equals to 0. 1 minute first to see all those, and you will also get some idea about that. Rank examples using minor. Example, find the rank of a matrix A. Solution. The maximal minor has an order 3 by 4, and the order is 3, and we found that the one obtained by deleting the last column -4 is not equal to 0. Hence the rank is 3. Here by using this you can also find the rank. So this is a very easy method, you can follow that. Example 2, find the rank of a matrix. The maximum minor has an order, so we compute the 4 minor of the first one. The det of the given matrix is 0. The other 3 are also 0. Since all minors of 3 orders are 3 are 0, the rank must be less than 3. We continue to look at the minor of order. The first one is the det is equals to -13 is not equal to 0. It is not necessary to compute any other minor and conclude that it is a rank of a matrix. Here the normal form. Normal form, a complex square matrix A is a normal form if A into A is equals to A into A star. If A star into A is equals to A into A star. If A star is a conjugate transport of A, then that is a matrix is a normal if the competes with its conjugate transport. A matrix A with a real entire satisfied A in A not, sorry, A star means A naught. A naught is equals to A transpose and is therefore normal if A transpose A is equals to A into A transpose. And in this normal form, you can use any kind of operation, whether it is a column operation or a row operation, in which operation you want to do, you can follow that. This is also easy to find the rank of a matrix. Thank you. I hope you all like my PPT presentation. Thank you.